Hi everyone. So today we'll be discussing on the topic online dynamic MST, right? So this is also one of the things where we can solve the dynamic chemistry problems. Yeah. So similar to Lichtenberg-Torop. So this is also one of the problems. So if you compare this algorithm, so we'll be discussing this algorithm basically. So if you compare this algorithm with the previous algorithm, there are certain things we'll not be doing within this algorithm, like deleting edges. So this is called as actually incremental. Basically, we call this one as online dynamic MST. This is completely related to the minimum spanning tree. Yeah. Previously we had solved on fully dynamic connectivity. Yeah, so also known as Hornday Lichtenberg-Torap algorithm, right? So there we have already seen the complete algorithm. Yeah, we have already solved one problem on it, and we had discussed the algorithm part as well. Now the main difference is here will not be making use of the deletion. So there we used to delete the edges and we used to go with the NTE basically. NTE also called as non-tree edge. So we would be fetching for the we had to fetch for the non-tree edge so that we can replace the path. Actually we can replace the path and then we used to query. That we used to do. Here we'll not be going with the deletion. This algorithm is also known as online dynamic MST. It's completely related to the minimum spanning tree and incremental. So there are certain problems which can be solved only with the online dynamic MST. It's completely different from this one, what do we call fully dynamic connectivity. Yeah, so it is usually the algorithm is called as fully dynamic this one, yeah, fully dynamic connectivity. The previous one, Lichtenberg-Torap. So this is known as online dynamic MST. Again, I'm repeating this one, I'm stressing on this. uh, Usually we call it as incremental basically. Yeah, there are certain things that is same as Lichtenberg, but a Lichtenberg-Torap algorithm, but there are certain things will not be implementing here. You'll get to know. So even though it is completely dynamic, it is completely dynamic in nature, right? So let's see what the definition part says here. So you'll get to know. I insist you to compare this particular algorithm after we solve the problem. You can just compare the algorithm as well as the problem that we solve with the previous algorithm. Yeah, that you can do actually. You'll get to know the difference, main difference. Yeah. So now let's do one thing. Let's move on with the this one definition part. Online dynamic MST, also known as incremental, maintains a minimum spanning tree. What it does, it maintains the MST or the minimum spanning tree while edges are added one by one. So we will be adding the edges one by one. So in the code, we'll be going with the add edge method or something like that. So usually we go with the add edge method itself. Yeah. So while edges are added one by one after each insertion, see, after each insertion of the edge, the MST is updated without recomputing from the scratch. There we used to recompute from the scratch. See, if you remember in the Lichtenberg-Torap algorithm, after this one, what do we call? After the deletion of the edge, we used to go for the this one. We used to fetch for the non-tree edge. If we get the non-tree edge, again we have to rebuild the tree. Yeah, again we had to rebuild the tree or the graph. So here what we'll do, after each insertion, the MST is updated without recomputing from the scratch. This is one of the huge advantages and the difference between these two algorithms. Yeah, it replaces heavier edges in cycles to keep the total weight minimal. Yeah, so this is one of the advantages. It replaces heavier edges in the cycles to keep the total weight minimal. So this is it about the algorithm. Now this is it for the definition part. Yep. Now let's do one thing. Let's discuss the algorithm or let's discuss the approach and then we can just move on with the coding part. Yeah. If everything goes well and if we get the desired output, and then we can just move on with the this one complexities part for the code that we have written. First, let's discuss the algorithm. Let's do that. So let's continue with the algorithm part. So we'll be going with the nodes 1, 2, 3. So I'll just show you the graph. So this is the graph that we'll be going with. The basic graph. Yeah, the graph actually. So for from 1 to 2 edge we have the weight for. From this one we have another edge just 3, right? So we have 3 nodes actually which are not connected. You can clearly see 1 to 2 is connected and 3 is different actually, which is having the weight 3. Yeah, so this is fine, I believe. So we will be going with we'll be starting with the nodes 1 to 3. So edge will be added one by one. So 1 to 2, we will be adding 1 to 2 with a weight 4. Yeah, we'll be adding 1 to 2 with a weight 4. Then we will be adding 2 to 3 with a weight 3. Yeah, so we will be adding 2 to 3, this part actually, 2 to 3 with a weight 3, the same thing. And we will be adding 1 to 3 with a weight 2 actually. So we'll be adding 1 to 3 as well with a weight 2. So if I say here, So we'll be going with a weight 2 actually. So this is fine. So which forms a cycle. You'll get to know that one. So cycle will be 1 2 3 1. Cycle will be 1 2 3 1. See, after inserting 1 3, so this one forms this one actually. Yeah. So first initial graph is this one, 1 to 2 with a weight 4. This one and 3 actually, basically 2 to 3 with a weight 3 and 1 to 2 with a weight 3. It has to be actually. We haven't added the edge. Initially we only have the three nodes 1 2 and 3 respectively. Now first after inserting the 1 3, see, you can clearly see here 1 3, this part actually. Yeah, 1 3 with a weight 2 actually, you can clearly see weight 2. So we'll remove the max edge 4. We will be removing the max edge 4. That's what we will be doing. Yeah. uh, Further, that's what we'll be doing. So we will remove the maximum edge 4 from the cycle. Yep. uh, so we'll add 1 3 2. Final MST would be 1 3 2 3 3. Yeah, so this one final MST will be 1 2, this one 3 3 2. Yep, so we can just say this one actually 1 3. Final MST would be 1 3 with a weight 2 and 2 3 with a weight 3. Yeah, 1 3 with a weight 2 and 2 3 with a weight 3 actually. Yep, so this is going to be the final MST. So these are the weights actually, don't get confused. Yeah, 2 to 3 with a weight 3. So this is the final MST actually after the insertion of 1 3 as well as the 2 3. So we'll be removing the maximum this one, what do we call, maximum weightage for this part. This part will be completely removed. Yeah, so this is fine, I believe. So the final MST, as I've showed, it would be 1 3 with the weight 2 and 2 3 with a weight 3, right? So this is what the algorithm does actually. Yep, I hope online dynamic MST is completely clear, right? So this is it. It's easier one comparatively with a Lichtenberg Torah. Yep, so what we'll be doing, we will first we will be adding the edge one by one, and after adding the edge one by one, we will be removing the maximum weight right, that forms the cycle. Basically, if the maximum edge weight forms the cycle, so we will be removing that particular edge. Yeah, and then the new cycle form, I mean new final MST would be, we will display the new final MST. That's what we'll be doing. So this is it for the algorithm part actually. So we are done with the algorithm. Now let's do one thing. We have discussed the approach part as well. Now let's try to articulate the same thing in the form of code. Let's do that. So let's do one thing. Let's start writing the code. First thing, we'll be making use of the buffer data and the print data. So I'll just import the input output package. So I'll just go with, yep, and also what happened here. Let me give the semicolon. And also we'll be making use of the different utilities. I'll just go with java.util.star. So this is fine. Next, within the main method or within the dynamic MST class. So this one, what we'll be doing? First, let's go with the edge structure. Why we will be going with the edge structure usually? We have to store the endpoints and the weight, right? Weight for the edge. So we have to store the endpoints as well as the weight. For that, I'll be going with the edge class. So I'll just go with class. Yeah, let me go with the edge, or yeah, I can just go with the edge or capital E. So within this particular class, we'll be going with the source, destination as well as the weight. So let's continue. Within the edge class, as I've said, we'll be going with the source, destination as well as the weight. For the source, I'll just go with the U. Yeah. For the destination, I'll just go with the V, and for the weight, I'll just go with the W. Right. So let's move on with the constructor part or the initialization part. Yeah. So I'll just go with the same thing, U, V as well as the W, or let me go with A, B as well as the C. Let me change the variable name. Yep. For the initialization, I'll just go with A, B, and C. Yeah. So let me do one thing. U, I'll just assign this one to A. V, I'll just assign this one to B, and W, I'll just assign this one to the C. I'll just come out of the constructor, this one entirely. Let me come out of the constructor entirely. Now we have to go with the total number of nodes. For the total number of nodes, I'll just go with static int n equals 4. In our case, we had 4 nodes, yeah, if you remember. So, or yeah, we are going with a different example. So we had 3 nodes, right? So 1, 2, 3 were the actually nodes. So let's go with a different example. Yeah. So I'll just go with the static here. So you can just go with the list of, let me pass the edge. Yep. So this is fine. Let me go with the variable MST. So this will be array list. Yep. So this is fine. Next, we will be going with the helper method DFS just to check if the path exists between the U, right? U to target actually, not just U to target. So it also stores the path edges on the result variable. Just remember this, we'll be making use of the result variable to store the path edge. So I'll just go with this one static boolean DFS method DFS, and it consists of the parameter U. Quite obviously, I have already said that it is used to check the path between U to target actually. Quite obviously, we'll be considering U as parameter and target as parameter as well. Yep, it's as simple as that. Now, let me go with the boolean here. Yep, visited, and I'll also go with list. Let me go with list here. List of E. So I'll just go with the path. So this is fine. Let me go with the list here. Sorry. Let me go with the list here. So this one will be list of E. So this is also fine. I'll just go with the resulting variable. So within this particular method, first thing, if that node has reached the target, actually, in that case, we have to store the path and we have to store the path and quite obviously we have to store the path as the node has reached the target. Also, we have to return the boolean value true. These things we have to do. Let's write that one within the if condition. Suppose if U equals target, in that case, what I'll do first, we have to store the path in the this one result variable, right? So I'll just go with the res dot add all. Let me make use of the add all. So this one will be path. Next, we have to return the boolean value true. Yep. So this is fine as per the discussion. So let me format the code once and let's move on with the further things. Now let's mark the current node as visited. As the node is visited, let's mark the current node as visited. Visited of U will be boolean value true. Next, what we'll do, let's iterate through all the MST edges. For that, I'll just go with a for edge, individual edge of this one MST. Yep. So within the for loop, the first thing, I'll just assign the next node or the next vertex to -1 initially. Yeah. So we are initializing next node to -1. Next, we have to check if the current edge is connected to the node U or not. Yep. For that, I'll just write the simple if condition. So this is simple. This will be E dot U. Let's check if it is equivalent to U. Then if it is, let's assign the next to E dot V. Yeah, it's as simple as that. Now, else, I'll just go with the else if directly here. Else if I'll just assign, let's just assign the E dot V to U. And let's assign next to E dot V. Yeah, E dot U. This is not we are assigning here. We are checking whether E dot V is equivalent to the U. If it is, then we are assigning the next to E dot U. It's as simple as that. Now we are done with this part. So now if we have the valid next node and if that particular vertex or the node is not visited, for that also we have to write the code. If next, if it is not equal to -1 and not of this one visited of next, then in that case what we will do, so I'll just go with the path dot add of E. Path dot add of E, in the sense we are just including the edge in the path. Yep, that's what we are doing. So next what we'll be doing, let's recursively search from next node. For that, I'll just go with if yes DFS actually. Let's recurse. What are the parameters that we need to include? Next actually, target, visited, path, as well as the result. Those are the parameters. Yep. So this is fine. In that case, we have to return boolean value true. Next, let's backtrack if not found. So I'll just go with a path dot remove. So it will be path dot size until the last one we have to backtrack, right? So I'll just go with a path dot size -1. Yeah, we'll be backtracking if not found actually. So this is fine. We are almost done with everything. The only thing that we are left is if no path is found, in that case we have to return boolean value false. So this is fine. Let me format the code so that the code looks good. Now we are done with this part. Yeah, we are done with this part. Next, let's do one thing. I'll just come out of this entirely. Now, as I've said, we have to add the edge one by one accordingly with the algorithm that we had discussed. For that, let's go with the add edge method. So I'll just go with the static here. So this one will be void add edge. So this is fine. We need 3 parameters. One is U, another one is V, and another one is W, nothing but weight actually. Yep. Sorry. What did I do here? Yeah. That bucket has to be here. First, let's go with a visited array for the DFS. We need the visited array for the DFS, right? Then we need the temporary path storage and the final path result as well. These three things we need. Yep. First, let me go with Boolean here. So this one will be visited equals new Boolean of n. Yep. So this is fine. Next, let's go with the temporary path storage. I'll just go with here list of this one. What do we call? E, this one I'll just go with a path variable. We'll be making use of the array list. And then finally, let me go with again list of edge. So I'll just go with a result variable. This will be we'll be maintaining the array list as well. So this is for the final path result. Yep. Next, let's move on with the further things. Now we have to check if the vertex u and v are already connected. Yeah. This we will be checking accordingly with what we had discussed within the this one when during the algorithm explanation. So I had said we have to check for the cycle. In our case, this one finally 3 to 1 formed a cycle, if you remember. Yeah, 1, 2 as well as the 3. So we connected 2 to 3 and 2 to 1 again that formed the cycle. 1 to 2, 2 to 3 and 3 to 1 that formed a cycle actually. So we removed the maximum, we removed the edge with the maximum weight next. Yeah. So we have what we have to do, we have to check if u and v are already connected, nothing but the cycle detection. For that I'll just go with the if this one dfs of what are the parameters u, v, visited, path as well as the result, this one itself. So if no cycle, then we have to directly add the edge. So I'll just go with mst dot add of, we have to add the edge, right? E of u, v as well as the w. So this is fine. Yep. Mm, yep. So this is fine. So next what we will do, here I'll just go with the s out, nothing but the system out println. So I'll just go with added edge here. So this one will be plus u plus, so I'll just for this one, I'll just make use of the hyphen here so that this looks good. Yeah. So I'll just go with plus v. Let's also concatenate the weight part actually. So I'll just go with weight within the string. This is fine. And also let's display the weight. Yep. So this is fine. Yeah, we are done with this part. Else if condition, else what we will do, else, so if the cycle is detected, then we have to find the maximum weight edge in the cycle so that we can remove that part. Yep, that particular edge. So I'll just go with max edge. It's simple. If you understand the algorithm part, actually, we are just articulating the same thing in the form of code. Yep. So I'll just go with a max edge here. So this one will be result dot get of 0. Yeah. So this is fine. Next, let's move on with the for loop. So I'll just go with e of result. So this is fine. Within the for loop, I'll do one thing. We have to update the maximum edge. For that, I'll just go with if here e dot w. So if it is greater than max edge, this part, then what we have to do, max edge dot w actually. Here in this case, let me assign the max edge to this one e. So this is fine. Let me come out of this one entirely. Now, if the new edge is better, meaning if we are having the smaller weight, if the new edge is better, see if w less than, we have already written this one, right? Or we have to write this one. Yeah. If new edge is better, nothing but the, if it is having the smaller weight, I'll just go with a max edge dot w here. In that case, we have to remove the heavy edge. Yeah. Or the, yeah, the maximum weight edge basically. We have to remove the heavy edge. I'll just go with a mst dot remove of max edge. Yep. Next, after removing, we have to add the new lighter edge. So I'll just go with the mst dot add of, we have to add the new edge, right? So for that, I'll just go with a new edge of, what are the parameters that we have? uv, nothing but the vertex along with the weight. Yep. Finally, let's print something for the interactiveness. I'll just go with the system out println here. So let's print the replaced edge here. I'll just go with replaced edge. Yep. So this is fine. Let me go with, yeah, max edge here. So this is extremely correct. So I'll just go with this one as well. let me go with a hyphen here. So this is fine. Then let's concatenate max edge or append the max edge dot v. So this is also fine. Mm, let let's go with this is absolutely correct with. So let me give here with again. So this will be, I'll just go with the u. Let me go with the hyphen again here. So this one I'm making use of hyphen and other stuff in the this one within the string so that this looks good actually, right? So within the yeah, this looks good. Nothing. So I'll just go with. So let me close this one as well. Yep. So this is it for the system out println actually. Yeah. Let me format the code once. Now we are almost done actually. Next, what shall we do? I'll just write the else statement here. So within the else, if the new edge is not useful, in that case, I'll just go with a system out println. So I'll just go with ignored here, ignored edge. So this is fine. Let me go with plus u. This is also fine. Plus, this one will be hyphen. Yep. Plus vertex v. Yep. So this is also fine. Let me format the code so that the code looks good. Now, yeah, let's move on with the further things. We are done with the coding part actually. Yeah, we are done with the coding part or the algo part. Just give me a second here. You miss anything? 1 second. So let's continue with the same actually. I'll just write here public static void main. So this is fine. Within the main method, let's do one thing. Let's consider the simple example. Yeah. So I'll just go with a add edge here. So let's go with uh let's go with three nodes actually. Three nodes as well as the weights between them. Yeah. So I'll just go with 0, 1, 4. So this is fine. Yep. So why this is showing yeah, this is not showing. Yeah. I'll just make this one small. Yeah. Now this has to show correct. Yep. So let me go with some more this one, some more edges as well as the weight. So I'll just go with, let me paste this one twice. So the edge will be from 1 to 2 with this one 3, and then let me go with one more added. So this one will be 0 to 2 with the weight 2 actually. Yep. So this is also fine. So I'll just go with s out here, system out println. So I'll just go with slash n. So let me go with the final MST. So this is also fine. So the next will be we have to print the final MST edges. So for that, I'll just go with a for loop. I'll just go with E of this one MST. Yeah. So within the for loop, what we'll be doing? I'll just go with the system out println of E dot U. So this one will be. So I'll just go with a hyphen. So this is also fine. Plus E dot V. So this is also fine. So I'll just go with yeah, colon here. This is also fine. Yep. I'll just go with a weight as well. Nothing but E dot W. So let me format the code so that the code looks good. Now we have to get the output. We have already considered the output part actually. So let's run the code. If something goes wrong, then we can debug. If everything goes right, actually, we can just discuss the output part. Yeah. Let me run the code. So you can clearly see here, we are getting the output added edge 0 to 1. We have added this one with the weight 4 actually. Yeah. So here by making use of the add edge method, this method actually, where is this? 1 second. This one you can clearly see here 0 to 1 with a weight 4 and 1 to 2 with a weight 3. Yep. So and the replaced edge 0 to 1 actually with a with actually 0 to 2. Yeah. We have replaced 0 to 1 with a 0 to 2 because it is having the weight 4. The maximum weight we are having here is 4. This edge will be completely replaced with a 0 to 2. Yeah, with a weight 2 actually. Yep. So see here, final MST will be 1 to 2 with a weight 3. 1 to 2, this one remains same actually, 1 to 2 with a weight 3. This particular edge 0 to 1 will be replaced by 0 to 2 actually. Yeah, 0 to 2 with a weight, this one actually 1 to 2 with a weight 3 we have considered. Yeah, so this one is fine. Yeah, and 0 to 2 with a weight 2. Actually, we have replaced this one. 0 to 1 with a 0 to 2. 0 to 1 we were having the weight 2. If you remember the example actually that we had considered while discussing the algorithm, we took the same example actually. We had considered the same example. We got the same output as the final MST. Yep, I had shown you the final MST, the graph part, right? So we got the same output there, 1 to 2 with a weight 3 as well as 0 to 2 with a weight 2. So whatever the code that we have written works absolutely correct here, right? So now let's do one thing. Let's quickly discuss the complexities part. Yeah, as we are getting the desired output for the code that we have written, let's quickly discuss the complexities part. Let's do that. So what will be the time complexity here? Just 1 second. Mm, Yeah. What will be the time complexity here? The time complexity would lead to pick of this one. What do we call? It completely depends on the number of nodes as well as the edges. N plus m into logarithmic n. Yeah. It would be n plus m into log this one n actually. Yeah, so this is the overall time complexity. Yeah, it completely depends on the number of vertices as well as the edges, right? So the overall time complexity would lead to big of n plus m log n. So what would be the space complexity? Space complexity you would have already discussed. The memory completely depends on a number of vertices as well as the edges, nothing but n plus m. So the time complexity and the space complexity for the code that we have written would lead to this one. What do we call? N plus m logarithmic n as well as this one big of n plus m, right? So this is it for the complexities part. Again, the time complexity and the space complexity would lead to big of n plus m log n and big of n plus m respectively. So this is it for the complexities part. Let's do one thing now. Now we have complete idea on the what do we call online dynamic MST. Yeah, online dynamic MST, which is incremental. We call this one as incremental. Yep. So there is the complete difference between actually a fully dynamic connectivity and the online dynamic MST. So just compare the algorithm, whatever we have discussed earlier, this one previous algorithm I'm saying actually. Um, the algorithm number 11 within the playlist, the compare that one with that one, actually it's completely different. Yeah, overall time complexity as well. Time complexity of the Lichtenberg Torap, actually it would lead to big of log square n. Yeah, here the time complexity has led to big of n plus m logarithmic n. Yep, the algorithm, uh, this one, what do we call? The problem that it solves is completely this one, the same actually. The problem that it solves is completely same, but but in a different way. Yeah, but the implementation is completely different. Yeah, we are having certain set of problems to solve the this one as well. What do we call online MST, right? And it's completely this one related to the MST, minimum spanning tree. Yep. So these things you have to keep in mind. So if when we solve the problem, when we implement the same algorithm within the particular problem that we consider in the future, now we'll be solving the problem, right? So compare that one with the previous problem that we have solved. It's completely different actually. We are not going with a deletion of the edge, and we are not replacing that one with a non this one tree edge, this one like that we have did it uh, within the this one Lichtenberg-Torap algorithm. Yeah, this is completely different. That's what I wanted to mention. This is completely different. Don't get confused with the Lichtenberg-Torap algorithm and online dynamic MST incremental algorithm. These two are completely different. That's what I wanted to say. Now let's try to do one thing. Let's try to implement the same algorithm within the problem. Yeah, let's do that. So let's do one thing. Let's continue with the problem. So this is one of the problem that can be this is one of the best problems to implement the online dynamic MST, right? Incremental part. Basically, we'll go with the same methods that we had implemented within the Lichtenberg-Torap algorithm. There are certain things like delete edges, uh, the whether the components are connected or not. For that, we went with a connected method. Actually, those kind of methods will not be making use of it within the online dynamic MST when we implement the online dynamic MST. So there are certain tweaks that has to be needed. That we will be going with as well, and there are certain things that will not be implementing at all. There is slight difference between the this one fully dynamic connectivity algorithm, also known as this one Homday, Lichtenberg-Torop algorithm, and online dynamic MST incremental algorithm. You will get to know when we write the code. First, let's discuss the question part. Yeah, just give me a second here. 1 second. Yep. So what the question states here, you can go through the question. Actually, it's very simple to understand. Yeah, it's very easy to understand, and all you have to know is you have to know the Lichtenberg algorithm. Actually, if you know the this one Lichtenberg-Torop algorithm, the implementation for the online dynamic this one MST will also be extremely easy. And one more thing, you get the opportunity to implement the offline dynamic this one MST. There are many problems to implement along with this one DSU rollback. Actually, you get uh, many problems. I wouldn't say many, but there are sufficient problems actually to solve this one online dynamic this one MST, or to implement the online dynamic MST. There are very few problems, means extremely rare. The problems are extremely rare. You might find 2 or 3 problems max. That too, if you try to implement the pure online dynamic MST, you will be getting the TLE. There are very rare. The problems are very rare. So, yep. So this is one of the problems we can this one. What do we call? We can implement the dynamic MST. Yeah, online dynamic MST incremental. Yeah, all go basically. So now let's do one thing. You can just go through the problem. I'll summarize the problem so that we understand even better, and it will be easier for us to solve the problem. Let's do that. Let me summarize the question. So what does the question states here? We have been given an weighted undirected graph. Yeah, we have been given weighted undirected graph. I'll just write here UG. So this states that the graph is weighted and undirected. Yep, we have been given a weighted undirected graph with n nodes. Yeah, with n nodes actually. Yep. So this is fine, I believe. We have been given undirected weighted graph with the n nodes and m edges. Yeah, and m edges. Yep. We need to find the subset of edges. Yeah. What we need to find here? We need to find subset of edges. Yep. So this is what we need to find actually. We need to find the subset of edges. Just remember this one. Yep. This subset should connect all the nodes. Whatever the subset that we get actually, that particular subset should connect all the nodes. Yeah, it has to connect all the nodes. Yep. So this is one of the important properties actually. When I say this subset should connect all the nodes, it has to form the spanning tree. That's what they're saying actually. Yep. This subset should connect all the nodes, nothing but the spanning tree. The total weight of the chosen edges must be minimum. In the algorithm, you would have this one seen actually. So we when the graph forms a cycle, we deleted the edge. We removed the edge actually with the maximum this one maximum weight, with the maximum weight actually, if you remember. Yeah. So the total weight. So I'll just write here TW. Sorry. Yeah. The total weight of the chosen edges must be minimum. Yeah. Must be minimum. Just remember this one. Yeah. They have strictly asked this one. It is guaranteed that the MST is unique. They have strictly said that it is guaranteed that minimum spanning tree is unique. So this is fine. So this is it for the question. All we have to do is we have to find the subset of the edges and make sure that the subset should connect all the edges, nothing but spanning tree, and the total weight of the chosen edges must be minimum. So this is it for the question. Let me read the question out loudly from the beginning. Just listen to this carefully. First thing, so we have been given a weighted undirected graph with n nodes as well as the m edges. We need to find the subset of edges. What we need to find? We need to find the subset of edges. The first thing, this subset should connect all the nodes, nothing but spanning tree. Yep. This subset first, we need to find the subset of edges. This subset should connect all the nodes, nothing but the spanning tree. The total weight of the chosen edges must be minimum. The total weights of the chosen edges must be minimum. And it is also guaranteed that the MST is unique. So that's what they have given in the question. All we need to find is the subset of the edges and make sure that the subset should connect all the nodes, and the total weight of the chosen edge must be minimum. Just remember this one. Let me delete this one. Yeah. So this is it for the question part. Now let's do one thing. Let's discuss the approach. Yeah. Let's discuss the approach, and later we can just articulate the same thing. Whatever we had, whatever we will be discussing in the approach, we'll be articulating the same thing in the form of code. And if everything goes well, and if we get the correct output, and then later we can just discuss the complexities for the code that we have written. First, as usual, let's discuss the approach first. So let's continue with the approach part actually. We are going with the same example or the same input that they have given in the question here, this one. Yeah. So input 4, 5, 4 indicates that we will be having the 4 vertex or the nodes actually, 4 nodes or the vertices, and 5 indicates that we'll be having the edges, 5 edges. You can clearly count here. We'll be having 5 edges. 1, 2, 2, 3, 1, 3, 4, 2 as well as the 4, 3. For the 1, 2, we have the weight 10. For the edge 2, 3, we have the weight 15. For the 1, 3, we have the weight 5. For the this one edge 4, 2, we have the weight 2. And for the 4, 3, we have the weight 40 actually. And the minimum span actually that we need to get here is 17. Yep. So with the calculation, we have to get the output 17. Let's see. Let's see the same thing in action. So now the same this one I have considered actually input for this one. What do we call? Approach as well. I have considered the same input or the example that they have given in the question. I've considered the same here, right? Let's move on with the further things. First key idea here would be, so what we will be doing, we dynamically maintain a tree using the linked tree. So we know the LCT from the Lichtenberg-Torap algorithm. So we have already made use of the LCT within the this one. What do we call? Lichtenberg-Torap algorithm or Homday-Lichtenberg-Torap algorithm. So we had used the LCT itself. LCT, ETT as well, Euler-Tour tree, and the other stuff. So we had made use of. So here we'll be dynamically maintaining a tree using the linked tree or the LCD. The entire thing is dependent on the LCT itself when it comes to online dynamic MST, that to incremental. So we have to go with the LCT at any cost, right? So we dynamically maintain a tree using the linked tree, nothing but the LCT. For every edge, if the nodes are connected, then we'll be adding the edge. If the nodes are connected, in that sense, we will be adding the edge. So we'll be making use of the add edge. So in the algorithm, we had written this one while writing the code. We had went with the add edge method, right? The same thing. If the nodes are connected, actually, in that case, we'll be going with add edge. So if they are already connected, in that case, what we'll do, we'll check the maximum edge in the path. Yeah. If they are already connected, then we'll check for the maximum edge because we have to remove the maximum edge, right? If it forms a cycle. If it is already connected, then we'll check maximum edge in the path. So then what we'll do, we'll replace it if the current edge is smaller. If the current edge is smaller, then we will replace it. Or if it forms a cycle, we'll be removing the maximum, the weight with a, the edge with a maximum weight actually. And we will be replacing it. If suppose if the graphs, suppose if the edge is already connected, we'll check for the maximum edge in the path and we'll replace it if the current edge is smaller. Current edge is smaller means current weight, the weight of the current edge is, if it is smaller, then we will replace the edge with a this one more weight actually. That's what we will be doing. It's as simple as that. Mainly just remember, we'll be making use of the LCT. LCT is the LCT plays a prominent role, or the linked tree plays a prominent role when we are writing the, or when we go with the, when we are dealing with the this one, what do we call, online dynamic MST algorithm, uh, also known as incremental. Right, so this is fine. Now let's move on with the further things. Let's move on with the graph part. See, accordingly with the edge they have given, we have actually in the this one you can clearly see 1 to 2 with a weight 10. Yeah, so 1 to 2 with a weight 10, this edge, this particular edge. Then we have 2 to 3 with a weight 15. You can clearly see here 2 to 3, this part actually 2 to 3 with a weight 15. Then we have 1 to 3 with a weight 5. So this part 1 to 3 with a weight 5. Then we have 4 to 2 with a weight 2. This is undirected graph. 4 to 2, this part actually with a weight 2. And finally, we have 4 to 3 with a weight 40. So this part 4 to 3 with a weight 40. Yep. So this is the graph. I insist you to pause the video and have a look into it. Graph, right? Graph part actually. Everything will be dependent on the graph itself. So first, whenever the graph problem is given, try to draw the graph, try to visualize whatever you are doing, right? So most of the things, when you see the graph, most of the things you'll try to remember, right? So most of the times you have, quite obviously you'll remember many things, right? You'll remember many things that is related to the problem actually. So that is the reason I insist you to draw the graph correctly. Whenever there is a graph problem, actually draw the graph. What are the things that we have to do? Just visualize in the form of graph itself that you have drawn, right? So this is fine. Now this is the graph actually. Accordingly with the input, this is the graph, right? So this is fine. We are done with this part. Yeah. So next, let's do one thing. Let's go with a step-by-step MST formation. Let's see. Yep. First step, we have the edge 1 to 2. They have given in the input 1 to 2 with a weight 10. See here, so 1 to 2 with a weight 10. Initially, it is not connected. So we will be adding this one to the graph. Yeah. MST will be 10. MST will be initially all the edges are isolated. So this will be 1, 2, 3, 4. Yeah. 1, 2, 3, 4. Right. So this is not connected yet. So we will be adding this edge 1 to 2 with a weight 10. That's what we will be doing. So MST will be 10. Yep, this is fine. Next will next in the this one input they have given 2 to 3 with a weight 15. You can clearly see here 2 to 3 with a weight 15. So we'll be adding 2 to 3 with a weight 15. See, 2 to 3 are also not connected. So we will be adding this edge with the weight 15. Yeah, you can clearly see this part. Yeah, 2 to 3 with a weight 15. So this is also not connected. We'll add. So now we have to add this one 1 to 2 as well as the 2 to 3. 1 to 2 is 10 and 2 to 3 is 15. 10 plus 15 leads to 25. Yeah, MST would become 25. So it's as simple as that. Next, let's move on with the third part. Nothing but we will be adding the edge 1 to 3. So this part actually 1 to 3, when I say we'll be adding the edge 1 to 3, this part 1 to 3 we have the weight 5. So this is also not connected actually. Yeah. So this 1 to 3 is already connected. Yeah. So because we already have 1 to 2 and 2 to 3. So 1 to 3 is already connected. So 1 to 3 is already connected. So cycle is formed. See here, this part. You can clearly see 1 to 3 is already connected. And this forms the cycle. Yep. This part. This quite obviously forms the cycle, right? So path we have is 1 to 2 and 2 to 3. So maximum edge among this we have here is 10, 15 as well as the 5. Among that maximum is 15. Yeah, among that maximum is 15. What we'll do, we'll try to replace 15 with a most smaller one. Smaller edge we have here is this one 15, 5, 10 and 15 is nothing but the maximum edge is 15 and the minimum edge is 5 here. So this is minimum and this is so this one is maximum. Yeah. So we will replace the maximum one with the minimum actually. When I say we'll replace the maximum with the minimum, so we will be replacing 15 with a 5. We'll be replacing the weight 15 with a weight 5 basically. So now the MST would be 25 plus 15 plus 5, right? So this would be 25. One second. So this one actually 25 minus 15. We are removing the 15 actually. We are replacing the 15 plus 15 with the 5. So basically this would become, just give me a second here. I'll just remove this one. One second. And let me make this one actually minus. Yeah. Yeah, 25 minus 15 is nothing but here in this case 10. 10 plus 5 would lead to 15. Sorry, I got confused here. I had written plus. So this is not the addition operator actually. We have to go with the minus. As we are removing the minus 15 and replacing that one with the 5. So we have to go with the 25 minus 15 plus 5. Yep. So this is fine. Now the output is nothing but 15 here, right? So the output is nothing but 15. One second. Yeah, the output is 15. Yeah, this is fine. Now let's move on with the final. It's nothing but 4 2, right? So 4 2, when I say 4 2, this one, 4 to this part. We haven't considered this one at all with the weight 2. Yeah, we are having the weight 2 actually. So oh, we are still having 4 3 as well. We haven't considered 4 2 and 4 3. Sorry, 4 2 with the weight 2. So 4 2 is not connected. It doesn't form a cycle and it is not connected. So we will add that particular edge. So we'll add that particular edge. So 4 2, the previous MST is nothing but 15, where it is. So this one. So when we added the path actually, 1 to this one, 1 3 with a 5. So we got the MST 15 actually. The previous one plus the weight for the 4 3. Weight for the 4 2, sorry. Weight for the 4 2, we are having 2. Here itself I have mentioned. In the graph also you can look at here. So this is 2 actually. Yep. So this is fine. This will be 15 plus 2, which would lead to 17. MST would become 17. Finally, let's move on with the final step. We are left with only one thing, nothing but 4 and 3. Yeah, 4 and 3 respectively. For the 4 and 3, you can clearly look at the graph. We are having the weight 40. This part actually. Yeah, we are having the weight 40. Yeah, 4 and 3 with the weight 40. So previously we have got the MST 17, the previous value plus this one. So this one 4 3 is already connected actually. You can clearly see here. because we have connected the 2 4, because we have connected the 2 4, it would be 1 2 2 4. This one 1 3 is already connected, right? So 4 3, so this would form a cycle, right? This would form a cycle, complete cycle. You can clearly see here, this would form a cycle. They are already connected, cycle formed. Sorry, I got confused. So now the path would be, path you can clearly see 1 to 2 2 to 4 actually. Yeah, 1 to 2 2 to 4 actually. Yep, so this is fine. uh Already connected. Yeah, this would be 1 to 2 2 to 4, and 4 to 3 basically. Yep, so this is fine. The maximum edge in the path is nothing but 10 5 and 2. You can clearly see this one 10 5. This entire thing forms up this one cycle, right? 1 to 2 2 to 4 4 to 3, as well as the 3 to 1. So the maximum path we have here is 10 5 as well as the 2. 10 5 as well as the 2, except 2 to 3. 2 to 3, we are not considering 2 to 3. So we are considering 1 to 2 2 to 4 4 to 3, as well as the 3 to 1. 1 to 2 we have the value 10. For the 2 to 4, we have the value 2. And for the 1 to 3, we have the value 5. See here, that itself, maximum edge in the path is nothing but 10 or 5 or 2, right? 10 or 5 or 2. So nothing is greater than the this one. What do we call? Uh, all are smaller values actually, right? All are smaller values. So we will ignore this one, and we will keep the this one MST 14 itself. We will keep the MST 17 itself, right? So we had to replace the maximum weight edge with the minimum one. So here we have 10 5 or 2. All the weights are smaller itself here, right? So the so we will be ignoring, and we will be keeping the final MST as the previous value itself that we got, nothing but 17 here in this case. So we got output 17. So the final MST weight is nothing but minimum spanning tree weight is nothing but 17. So this is the output that we need to get. Yep. So this is the output that we got actually. Yep. And the output that we need to get here is 17 as well. They have correctly mentioned here. They have strictly mentioned here. We have to get the output 17. Yep. So the output that we got here is 17. Yep. The output that we got here is 17. So whatever the this one approach that we went with works actually absolutely correct. So here in this case, we are done with the approach part. Yeah, we are done with the approach part. Let's do one thing. I'll just remove. So let's do one thing. Let's try to articulate the same thing in the form of code. So we will be going with a LCT. Code will be little big because we'll be going with a LCT. Yep, linked tree actually. Online dynamic MST incremental one basically uses LCT itself. Yep. So we'll be making use of the LCT, and let's try to articulate this exact same thing in the form of code. Let's do that. So let's do one thing. Yeah, whatever we had discussed on the approach, let's try to articulate the same thing in the form of code. Yep, let's do that quickly. So just give me a second here. Let me open the IntelliJ. Yeah, let me minimize this. I'll just close this one. Let me open this one. Yeah. So yep, now let's start writing the code. First thing, we'll be making use of the buffer header and the print writer. So I'll just import here. We'll be making use of the different utilities as well. So let me import the utility package, and also let me import here input output package, as we'll be going with the this one. What do we call? Buffer header and the print writer. So this is fine. Now let me do one thing. So first thing, let's go with a node or the edge. Accordingly with the algorithm, we have to maintain the edge or the node class. Yeah. So I'll just go with static here, class node. So within the node class, why we are writing this particular class actually? So here each node in the link, we will be considering each node in the linked tree, as we'll be going with the LCT or the linked tree. So we'll be going with the left child, right child, as well as the parent in the split tree. For that, I'll just go with the node here, left, right, as well as the parent. Next, we'll be going with a flag for the lazy propagation as well. So we'll be going with a lazy propagation. For that, we'll be going with a flag. So I'll just go with a boolean here. So the variable that I'll be going with is reverse. Yep. So this is fine. Now, this is nothing but the REV is nothing but the reverse path. Yep. So we know this one from the algorithm. Now, so let's maintain the variable value as well as the max. Value is nothing but the edge weight. Max is nothing but the max weight in the subtree. Yep. Max weight, we have to get the max weight if you want to replace the edge. So we need the max edge, right? So this is fine. I'll just go with the int value as well as max. So this is fine. Next, so let me go with node. Let me go with a max node actually. max node variable. Max node variable actually it just acts as the pointer to node having the max value. Yep. Now this is fine. Let me go with the node u comma v. Yep. So this is fine. Now we are done with this part. I'll just come out of this one entirely. So let's go with the isRoot method. So I'll just go with a static. So Boolean, I'll just go with isRoot. Yep. So let me go with this one. Node X actually. Node X. So this is fine. So within the isRoot method, I'll just go with return here. So I'll just go with x dot p here if it is equivalent to null, or I'll just go with x dot p dot l. So if it is not equal to x, and I'll just go with x dot p dot r here, not equal to x. So this is fine. Let me come out of this one entirely. Now let's move on with the push method actually. So we have to push the lazy reverse operation. So this is just for the intense optimization. So I'll just go with a static here. Void push. So this is fine. Let me go with a parameter x. So within this particular method, first thing, let's check if suppose x not equal to null, and so I'll just go with x dot reverse. Then so let me go with the t equals x dot l. uh, Let me go with x dot l equals x dot r. So we are maintaining the temporary variable here. We are swapping the children basically. That's what we are doing. So that is the reason we are maintaining, or we are going with the temporary variable. Let's assign the right x dot r to the temp. So this is fine. Next, let's write the simple if condition again. So this one will be x dot l, nothing but the left. If it is not equal to null, in that case, I'll just go with a x dot l dot reverse, nothing but the reverse edge here. So this one, let's go with the XOR actually. Yeah, XOR true. Yep. So the same thing, let's do it for the right side. X dot r, if it is not equal to null, x dot r dot reverse XOR the same thing, XOR true. Yep. So this is fine. Finally, we have to clear the flag. For clearing the flag actually, I'll just go with the false, not the true here. Let's go with the Boolean value false. This is it for the this one push method. Now we are done with the push method. Let's do one thing. Let's move on with the pull method. Yeah. So I'll just go with the static here. Why this is showing in this way actually? Yeah. I have done the mistake here. So I have to start from here. 1 second. Yeah. Yeah. I'll just go with the static here. Void. So let me go with the pull method actually. Yep. Let me go with the pull method. Pull the same thing, node x. If x equals this one, this is not required, so I'll just go with step by step. Let me tell you. So we need to update the maximum information, so we are going with the pull method first thing with the parameter x. So first thing, let's start with its own value. So I'll just go with x dot max here. X dot max, let me assign this one to the x dot value, and let's go with the x dot max node. Yep, this one. I'll just assign this one to the x. This is fine. So x itself is max initially, right? So this is fine. Now we have to check the left as well as the right subtree. That's what we have to do within the pull method. For checking the left subtree, I'll just go with x dot l, nothing but the left actually, left subtree. If it is not equal to null, and so I'll just go with x dot l. Instead of the reverse, I'll just go with a x dot l dot max. If it is greater than x dot max actually, in that case, what I'll do. So we are checking for the left subtree, right? Fine. Should close the this parenthesis here. Right. So within the if condition, first I'll just go with x dot max. Let me assign this one to x dot l dot max actually. So this is fine. And also I'll just go with x dot max node. So this one is fine as well. So this one will be x dot l dot max node. Yep, it's as simple as that. Now let's move on with the further things actually. This will be if x dot or same thing. Let me copy the same thing actually and make the necessary change for the right subtree. So here one thing is I'll just go with the x dot r if it is not equal to null, and x dot r dot max here. Instead of the left, I'll consider right. So if it is greater than x dot max, then x dot max we will be assigning this one to the right one. Yeah, x dot r dot max here. So this is fine. X dot max node. So this one will be x dot r dot max node. Yep. These are the changes that are needed actually. Let me format the code so that the code looks good. Now we are done with this particular method. So this is it for the pull method. It's simple. Yeah. Now let's go with the main thing, nothing but the rotate method actually. So I'll just go with the static here. Static. So let me go with void. It doesn't return anything. So I'll just go with rotate here. So let me go with node x. Yep. Within the rotate method, first thing, let's do one thing. I'll just go with a variable p here. So I'll just assign this one to the x dot p and also g. Let me go with p dot p. So this is also fine. And let me go with push actually. Push of p. So this is also fine. And let me go with a push of x as well. Yeah. So this one will be push of x as well. We are just going with the parent and the grandparent. We have went with the parent and the grandparent already, and we went with pushing the lazy uploads, push of p and push of x. We have successfully done that. Now we have to go with a we are going with a rotate method. Inside that we will be going with the right rotation, or we have to perform right and left rotation. That is the reason we are going with a rotate method actually. Yeah. First, let's do one thing. First, let's go with the right rotation. For the right rotation, I'll just go with if p dot l, if it is equivalent to x, then let me assign p dot l to the x dot r. So this is fine. And let me write the simple if condition here. If x dot r, if it is not equal to null, in that case, I'll just go with x dot r dot p. Let me assign this one to the p. Yep. So this one will be x dot r. So this is fine, man. Yeah, we are done with this part. Now I'll just assign x dot r equals p. Yep. So this is fine. Else, so within the else, I'll just go with p dot r equals x dot l. So this is also fine. Let me go with a simple if condition. If x dot l, if it is not equal to null, in that case, x dot l dot p, let's assign this one to the p, which is absolutely correct. And x dot l will be assigning this one to the p, not x. Yep. So we are done with the else part as well. Let me come out of this one entirely. Now, after the right as well as the left rotation that we have performed, now we have to update the parent pointers. Parent pointers, nothing but the p dot p. Let me assign this one to the p, and also x dot p, the child one. So this one will be, we will be assigning this one to the g. Now we have to connect to the grandparent. To connect to the grandparent, I'll just write here if g not equal to null. If g is not equal to null, in that case, what we will be doing, I'll just go with if g dot l actually, if it is equivalent to p, in that case, I'll just go with g dot l equals x. And also one more thing, let me go with the else if here. Else if g dot r, if it is equivalent to p, then g dot r equals x. Yep. So this is it for the mm, we are almost done with the rotate method. We are left with only one thing, nothing but we have to update the values. Nothing but again, we have to update the values. So I'll just give here full of actually p, as well as we have to go with the this one for x as well, right? So I'll just go with full of x. Yep. So we are done with this particular method. Let me format the code so that the code looks good. Now let me come out of this. So we are done with the rotate method. Let's go with a splay method. So we have to bring x to the root. If you know the Lichtenberg algorithm, actually, there also we did the same thing. Actually, we have to bring the x to the root. Actually, yeah. So let's go with a method splay. Right. So I'll just go with the splay here. Sorry. Yeah. Splay with a parameter x. Actually, I'll just go with a parameter x. So within the splay method, first thing I'll just go with not the pull. This time we'll be going with a push. Actually, yeah, we have to push. So here push of x is fine. Then I'll just write while not of this one will be is root. Yep, is root of what? Is root of x. So this is fine. Then let me go with a node of p equals x dot p, and let me assign the g to p dot p. So this is fine as well. Now let's do one thing. Let's go with a simple if condition here. If not of is root, if not of is root of p actually. In that case, what we'll do, let's go with a simple if condition. If p dot l, if it is equivalent to x, so this one we will be checking with, sorry, this one, let's check the value. Is it same as g dot l equals p? Again, the comparison operator we have comparison operator we have to use. So in that case, I'll just go with a rotate of p. Yeah, we are just going with a zigzag rotation here, right? So else I'll just give rotate of x, not the p dot l actually. Let me give x here, right? We purely went with a zigzag rotation, and here also we have to mention rotate of x actually. Yep, so this is also fine. And finally we are left with only one thing, nothing but we have to go with a pull of x. Yeah, not the push actually, pull of x. So let me format the code so that the code looks good. So this is it for the display method. We are done with the display method. We have successfully we have successfully brought the x to the root. Yep. So now we are done with this particular method. Let's move on with the access method. Access, within the access method, what we'll be doing, we will be exposing the path to root. That's what we'll be doing. Yeah, let's expose the path to root. So I'll just go with static here, void access here. Again, the same thing. I'll just go with a parameter x. So first thing, I'll just go with a node last equals null. So let me assign the last to null, and let's go with a simple for loop. So let me go with node y equals x actually. So what happened here? Yeah, this is fine. Node y equals x, y not equal to null, and y equals y dot, not l actually. It will be p. Yep. So within this for loop, what I'll do, I'll just call this play method that we have written, play of the variable y we have to pass. Now we have to cut right and attach the previous. Yeah, that's the reason we call it as link cut. Yep. So I'll just go with a y dot r here, and let me assign this one to the last. So this is fine. And let me call the this one full of y, and finally let me assign the last to. Yep. So this is fine. What I'll do, let me call the display method here. Display of, let me call the variable x. So this is fine, I believe. So this is it for the coding part. Sorry, this is it for the access method. So let me come out of this one entirely. We are done with the access method as well. Now, still, if you remember, actually, we have to go with the make root. Make root method is needed because we have to make x as the root of the tree. Now, for that itself, we have written the this one. What do we call? Display as well as the this one. Rotation, these kind of this thing. We have written just to make the x as root. For that, I'll just go with a static here, void. I'll just go with make root. So this is fine. I'll just go with the node x. So this is fine. Within this method, make root method, I'll just go with access of x. So this is also fine. And let me go with the XOR here. So let me go with x dot rev here, XOR. So let me go with the true. So this is fine. We are just reversing the path by making use of the XR. X dot rev is nothing but the reverse path. So we are going with x dot rev equals true actually. So this is fine. We are performing the XR. After making the x as root of the tree, so let's do one thing. So let's move on with the next method, nothing but this one. What do we call? Find root. So after making the x of x as the root of the tree, we should be able to find the root of the tree. For that also, we'll be writing the method named find root. So I'll just go with a node here. So this one will be find root. Yep, the same parameter x actually within this particular method. Again, let me call access of x. So this is fine. So I'll just write the simple while loop here. While of, so if it is true, then in that case, what we will be doing, sorry, in that case, let me go with a push of x here. Yep, push of x. Then if x dot l, if it is equal to null, in that case, what we have to do, let's break from here. Let's break from here in the sense, let's exit actually. Yeah. So then I'll just go with, or let's assign x to x dot l. Yep. So this is fine. Let me do one thing. I'll just go with a display of x. So this is fine. And let me return X. Yeah, let's return X. So let me format the code so that the code looks good. Yep, so this is fine. We are done with the find root method. I'll just come out of this one entirely. Now let's do one thing. Let's go with the link method. So I'll just go with the static. So let me go with void. I'll just go with the link. So I need two parameters. One is node u and another one is node y. So here instead of X, let me go with a u and another one is node v. Actually, X and Y also we can go. Usually we consider this one vertex, this one. Yeah, for the vertex we consider u and v, right? So we'll be going with a u and v respectively. Yep, so this is fine. We are going with the link. So these two things are not required. So I'll just go with a, let me call the make root method here, make root of u, and also let me assign u dot p, nothing but the parent, to v. Yep, so we are done with the link method as well. Yep, now let's go with the cut. As we have went with the link, now let's go with the cut actually. So we call it as link cut itself, right? So I'll just go with static here. So let me go with void cut. So I'll just go with node u as well as the node v for this as well. So now we'll be calling make root of u here as well. We need that one. So I'll just go with the access of this one. Let me pass the variable v. And now let me go with a simple if condition. V dot L, suppose if it is equivalent to the value, this one, vertex u, then I'll just set the V dot L dot P to null actually. And the next step would be V dot L to null as well. And the next step would be pull this one, pull of V. Yep, so this is fine. Let me format the code and so that the code looks good. Now let me come out of this one entirely. We are done with the cut method actually. Yeah, we are done with the cut method. So next let's do one thing. Let's move on with the further method, nothing but the query max. For the query max method, I'll just go with the static here. So let me go with node. I'll just go with query max. So this is fine. Let me go with the parameter u as well as let me go with the parameter v. Yep, so this is fine. So within the query max actually, all we have to do is we have to consider the max edge in the path UV. The edge max path, max edge in the path UV. Right. Again, for this we need actually the same thing. Make root of u. This one. Yeah. Let me paste this one over here. And again, we need access of v. So let me copy this one and paste it over here. And next, we have to return maximum edge in the path UV, right? So I'll just go with return here v dot max node. This one, yeah, v dot max node. It's as simple as that. Very simple. Yeah, link cut as well as the query is very simple to understand. Now we are done with the this one. We are done solving the problem. Actually, we are. This is it for the problem. So if you know the linked tree actually LCT, it's very simple to implement actually. If you know that LCT, or either if you know this one Lichtenberg algorithm as well. So there are certain changes that are required. We shouldn't be going with the delete and other stuff, delete, connect and other stuff. If you know that algorithm, so this becomes very easy. Yeah, I can assure that this is very easy. If you know the Lichtenberg algorithm, it's easy to implement this algorithm, online dynamic MST incremental one. Yeah, it's simple when it compared to the when we compare the same thing to the this one Lichtenberg Torap algorithm. Now we are done with this part. Let's do one thing. Now let's move on with the further things. Yeah, so we will be going only with the this one. We are left with this one. What do we call input output part? Yeah, so that one will be mentioning that one within the, or that we will be writing within the main method. So let me copy paste that one. Just give me a second here. So let me do one thing. I'll just come here and let me paste this one over here. So this main method from here basically. Yeah, from here, from the line number 137 to line number this one. What do we call? 201 actually. So this one, let me explain this one extremely fast. So this one buffer reader and the print writer, it's related to the input and the fast this one fast input, buffer reader, fast output, print writer. Then we are just going with a string nm here, buffer reader dot readline br, a buffer reader variable we have made use of. So this part is nothing but we are reading n and m accordingly with the input. So if I open the Chrome, see here we have to read this one first line n and m inputs, right? So n is nothing but the number of vertices, m is nothing but the number of edges actually. We have to read both. So here. Yeah, 1 second. Let me open the IntelliJ. We have to read NM, so we are successfully we have successfully read the NNDEM. So after reading NNDEM, so we have to create the node extra for the edges. We have to create the node extra for the edges as well, right? So I have written this one. Next, we are going with a for loop. Within the for loop, what we are doing, we are initializing the node and default weight. We have to do that one. Yeah, we have to. We are initializing the node as well as the default weight for that initially, right? So that's why we are we have initialized the node and default weight. Next, let's move on with the further things. So this is nothing but the edge index as well as the MST edge index. This is the index for the edge nodes. We need the index for the edge nodes u and v. We need the index, right, for the particular edge and this one for the particular nodes. So this is nothing but edge index. We have made use of it for the same sake, for that sake itself. And result we have to store. We have to store the result somewhere. So we are going with the result variable MST here. As we are calculating the minimum spanning tree itself, uh, I have went with a result variable MST instead of the RES or the ANS. Usually we go with the result or the answer, right? So I went with a, as we are calculating the MST, I have went with the resulting variable MST. So this is fine. Now we went with a for loop. Next for loop is nothing but we have to read all the edges. We have to read all the edges. So we are doing the same thing actually until here. So this is fine. Next, NU and NV is nothing but here node U as well as the node V. So this we know. Let's move on with the further things. Now I have written simple if condition. Suppose if the this one edges are not connected, we have to create the edge node. Yeah, if the initially all the this one vertex will be isolated, and if suppose if the edges are not connected, in that case we have to create the edge node. That's what we are doing here, right? So now I have given we have made use of the link of nu comma e and link of n this one e comma nb. We are connecting the this one u to u edge, and we are connecting the edge v and u edge. So we have to connect the this one two nodes, right? We have to connect the edge. Basically we have to connect the edges and make it as a node. So we are connecting the u edge and we are connecting the this one edge v. After that one we are adding the weight. For adding the weight we are going with mst equals mst plus weight. Yep, within the else, if we have found the max edge in the path, suppose if we have found the max edge in the path, in that case if we still have the better edge, yeah, if we find the better edge in the future, in that case we have to remove the old edge and we have to replace that one. Yeah, accordingly with the algorithm we have discussed this one in the approach as well, and we had discussed that one in the algorithm part when we discussed the algorithm as well. Yep, we suppose if we have found the better edge, in that case we have to remove the old edge and we have to replace the or then we have to add the new edge, or the old edge has to be replaced by the new edge, right? So that's what we have done here until here. So this is fine, I believe, until here actually. Yeah, until here basically. Then we need to connect the new edge, right? So we need to connect the new edge in the graph, right? For that we have written here this one. We are just connecting the new edge nu to e to this one NV. So this is fine. Finally, after that, after connecting the new edge, we have to update the this one MST, minimum spanning tree, right? We have to update the MST. So that's what we are doing here. MST equals MST plus weight minus maximum edge dot value. So this one is completely dependent on the this one max edge. If we have the max edge and if it is replaceable by the edge that is having the small weight, actually in that case we have to write this amount of code actually from here basically, if conditions and other stuff that we have written. It is completely dependent on that. Now this is fine, I believe. Yep, so this is it for the main method. Actually most of the input output operations we have done within the main method itself. So it's 90% it is related to the input output itself. Yep, so this is fine. Reading this one, but mostly related to the buffer data and the print data. We have to read the input and other stuff, that whatever the changes accordingly to the input output they have asked. Usually we write it within the main method. And the main logic, usually I prefer to go with the solve method. How do I solve? It's left to you to solve, but my structure is I'll just go with a I'll segregate into different methods and then try to solve the problem. That's what I do actually, in my opinion. Yep, so it's better because you'll understand everything clearly when you look into the code. So usually I go with the whenever I'm giving contests or this one wherever. So if you are given the contest, whether in the lead code, this one, whether it is in the code forces, code chef, coder, anything, any this one, or if you are solving in the online judges, anything, SPOJ, uh, DMOJ. So anywhere, if you're solving the problems, so in that case, usually I go with a single letter variable naming. Yeah. So I I have to type a lot. So usually I go with a single letter, this one. What do we call? Single letter variable naming. Usually I go with a single letter variable naming. So other than that, I try to segregate into different methods and then try to implement the this one solution, right? So that we get to understand the problem better, and whatever we have implemented, that particular method name, you have to keep that one clearly. So whenever we write the code, or if we the code readability would be better if we write in that way. So I feel that the code readability will be better if we segregate into different methods and if we write the code. So yeah, that's what I feel. So this is it for the coding part actually. Yeah, this is it for the coding part. We are done with this part. Now let's do one thing. Yeah. So if everything goes well, we have to discuss the complexities part. We are left with the complexities part, right? So first let's check for the output actually, and we have to submit the code. These two things we have to do first. So let me run the code. So yeah, we are so we have to give the input actually. Let's see. I'll just open the Chrome. Yeah, let me copy this one here. Let me copy. I'll just come here. Let me paste it over here. Let me hit the enter. You can clearly see here the output that we are getting is 17, which is absolutely correct. Yeah, which is absolutely correct. So we are getting the correct output, meaning we have written the code correctly. So let me copy the entire code here. Let me copy the entire code. I'll just open the Chrome. There is something called submit solution here in the SPOJ. There is something called submit solution here. Let me click this one. Yeah. So I'll just select here instead of the ADA, I'll select this one, Java. So where is Java? So you can clearly see here Java with a hotspot. Well, yeah, let me do one thing. I'll just remove this one and let me paste the code and let's make some changes. So here, let me remove this. This is not required. This is completely related to the IntelliJ. And here, let me make this one main and public is not required. Yeah. So class main is enough actually when we're submitting. So yeah, one more thing for this particular problem, it will not show accepted. Instead, it will rate the this one. It will rate from 0 to 100. If we get 100, it is completely accepted. So if we get 40, 50, something like that, certain test cases are passing and certain test cases are failing, right? So let's check. Let me submit here. Let me hit the submit. So here you can clearly see compiling. Let's wait for some time. So we have to get this 100. So running 0, you can clearly see here. Let's wait for some time. 9.09. Time this one. So if it is 9.09, actually we have to get 100% here. So if it is 9.09, meaning so the output is somewhere we have done something wrong actually. Let me reload this one. We're left with 9.9 itself, right? Let's check what we have done wrong actually. Yeah. So let me open this one. Yeah. 9.09 means many test cases are failing actually. Let's check the same. So what mistake I have done here is, let me come to the query max here. So just give me a second here. Yeah, query max, what is happening? See, I tried to copy these two things actually, make root u, and we need the access path. We need the access path actually to the v. So from u, we need the access path from u actually to the v, right? So we have considered the root u. We need the access path v. So I copied this one instead of this one here. I have pasted the make root of this one of u again. So let me change this one to the access of v. Now let me format the code. So now again, let me copy the same thing here. So I'll just open the Chrome. So here we were submitting, right? So where did it go? So yeah, I'll just go to the question again. Minimum spanning tree. Let me hit the submit solution. Yeah. So this time we have already selected the Java. So let me paste the code and make the necessary changes. So let me remove this one. This is not required. So again, let me change this one. Let me remove the public as well. I'll just go with the main here, method main. So now let me hit the submit. Yeah, I hope this time we get 100%. Let's see. Let's wait for some time. So this time it has to work. So while pasting this one access of v, instead of that I had pasted make root of u itself. So that's completely wrong. Actually, we'll be getting the, see here we are getting the 100, basically 100 in the sense all the test cases are working correctly. So let me go to the profile here, submission history. You can clearly see here we are getting the 100, meaning whatever the solution that we have submitted is absolutely correct. Actually, whatever the solution that we have written or whatever we have submitted, it is absolutely correct. Yeah, you can just ed on it here. I'll just click the ed on it, and you can just check this one in the editor. Yeah, you can just check the code in the editor. Yep. So this is fine. We have successfully written the code. Yeah. So let me do one thing. We have successfully written the code, and yeah, we have got the AC, right, accepted, or the code is 100% working. So this is fine. Now we are done with the coding part. We are left with only one thing, nothing but we have to discuss the complexities for the code that we have written. Let's quickly discuss the complexities part actually. Yep. So let's do that. Give me a second here. Yeah. So what would be the time complexity here? The time complexity for the each operation, actually, we are going with link. We went with the cut method as well as we went with the query. If you remember, we went with link, cut as well as the query, right? So for all the operations, it would lead to big of logarithmic n. The time complexity would lead to big of log n. Yeah. So this is fine, I believe. The time complexity for the link, cut as well as the query method would lead to big of logarithmic n. So total edges in the question, in the input, we have is m, right? So the total edges here we are having is m, and so overall time complexity would lead to, as the complexity for the each method link, cut as well as the query would lead to big of log n, and we have the m edge, right? M edges meaning total edges. So total edges is m, so overall time complexity would lead to this one because m into log n, right? So this would turn into, total complexity would turn into because m into log n. Yeah. So this is the time complexity actually. So this is the time complexity. Overall time complexity would lead to big of m into log n. So what would be the space complexity here? Space complexity would lead to big of n plus m. You would have already guessed this one. This is completely the memory or the space is completely dependent on the nodes as well as the edges actually. The number of nodes or the vertices that is present, nothing but n, and the edges, right? Nodes plus edges will be stored in the memory. So the time complexity and the space complexity for the code that we have written would lead to big of this one m log n as well as the big of n plus m respectively, right? So this is fine. Now we are done with this particular algorithm, right? So we are done with this algorithm. Yep. Let's do one thing. Next, what we will be doing, we will be discussing on the topic dynamic transitive closure algorithm. So this is one of the important algorithms actually. So we'll be discussing on the topic dynamic transitive closure algorithm. Yep. We have successfully discussed fully dynamic connectivity or the Homday-Lichtenberg-Thorup algorithm. And now we have discussed about the online dynamic MST algorithm as well. Yep, these two things we have got the opportunity to implement the same thing, the same algorithm within this particular, this one, what do we call problem. Yeah, within this particular problem, minimum spanning tree. Yep. So this is fine, I believe. We are, I hope the online dynamic MST algorithm is completely clear. Next, as I've said, we'll be going with a dynamic transitive closure. Yeah. So for now, this is it. Thanks for watching, guys.